It's a sunny day, an outdoor cafe. I have my dinosaur coffee mug. We can talk about classification. Now, when we talk about regression, we saw that we could use very simple metrics like the mean square error, for instance, or the root mean square error. For a classification, though, it's slightly different. So let's look at an example. Imagine that we have this population here in blue that contains gastropods, bivalves, and quartz crystals. We have, in this case, 7 of each class. So that means a total population of 21. Now, the precision can be calculated by the ratio of the true positive over the true positive plus the false positive. So the terms true positive, false positive, true negative, and false negative refer to whether or not the prediction of the algorithm is correct or incorrect. So now, for argument's sake, let's create a very dumb algorithm that we'll call dumb predict. So we define dumb predict. And what this algorithm does is it returns bivalves. So in other words, whatever the class of the instance we will feed to this algorithm, it will tell us it's a bivalve. So let's look at the precision of that algorithm. Well, the precision is easy to compute. It's essentially 7 over 7 plus 14, the total number of classes. And so we come with a precision of 33.3%. Now is a good time to talk about class imbalance. Remember that in the example I showed you, all the classes are very balanced. We have 7 instances of each one of those, so we get to a precision of 33% for this particular random algorithm, which is less than 50% of the time we will get it right. So it's actually a terrible performance, but of course we know this is a dumb algorithm. So what happens when the classes are not balanced? Well, in this case, we have very imbalanced classes because we have 19 bivalves for 1 quartz and 1 gastropod. The total is still 21. Now, if we compute the precision of this particular algorithm, if you try to predict whether or not the organism that you give is a bivalve, we get a surprising result. We essentially get 90% precision. Wow, 90% precision, that's fantastic. It's the world's best algorithm, except that it's a dumb algorithm. And the only reason we get such a high precision is because our class imbalance is so strong. So in other words, if you write an algorithm that predicts that you get a bivalve, you will be correct 90% of the time. So we need to use more sophisticated metrics to look at the precision, accuracy, the performance of those classification algorithms. One such algorithm is accuracy. Now, accuracy is defined as the ratio of the true positive plus true negative over the true positive plus true negative plus false positive plus false negative. So in other words, all of the predictions. And that is actually a metric you can use alongside precision. Another one is recall. Now, recall is simply the ratio of the true positive over the true positive plus the false negatives. But what if you want a metric that actually looks at all of these different ratios together? Well, there is such a thing, and it's called the F1 score. And the F1 score is simply twice the recall times the precision over the recall plus the precision. And it gives you a very compact way of looking at all of these numbers together. But sometimes it's actually easier to plot things in a more visual way. So something that is often used is a confusion matrix. The term alone, confusion matrix, is fantastic. Why would you want to use confusion to understand your data? But really, this is a useful technique. In a confusion matrix, we essentially plot the true label on the vertical axis. So that's what the samples actually are. Remember, this is for supervised learning, so we know what the labels are. And on the other side of the matrix, we put the prediction. So those are the predicted label. Now, this diagonal here is where the true labels and the prediction match. So in other words, when we have a true positive. So what happens now if we use this confusion matrix with our balanced classes, the 7 of each class distribution, but of course with our dumb classifier that always tells us it's a bivalve. So when we do this, what's interesting is that we put in the matrix the different values of the predictions, and it's immediately visible that we have a problem, because we see that we've predicted 7 out of 7 bivalves correctly, but we also see that we've predicted 0 out of 7 quartz correctly or gastropod correctly, and instead we've predicted them as being bivalves. So the confusion matrix gives you visually a lot of information immediately. That's why it's so useful. And if we do this with the imbalance classes, we get the same result. We see immediately that we have 18 bivalves and they've been correctly predicted. However, the gastropod and the quartz crystal are incorrectly predicted to be bivalves, and the imbalance in the class is immediately visible in the confusion matrix. So these metrics that you can use to check how well your algorithm is doing are extremely useful, and you always want to check with cross-validation, for instance, how well your training set is predicted and how well your test set that you left aside is doing as well, because that way you can spot things like overfitting, underfitting, or well-balanced algorithm after training.